Hi, everyone. We'll get going with our program in just a second, so if you could head back to your seats. There's some seats up front. This is just like the classroom. If you're coming late, you gotta sit in the front row here. I don't think Scott will call on you though, so you don't have to worry about that. So, you don't know. It might be audience participation. Okay. Well, it's my pleasure to welcome Dr. Scott Steinschneider as our keynote speaker this morning. Dr. Steinschneider is an associate professor at Cornell University in the Department of Biological and Environmental Engineering. His research applies varied modeling approaches to evaluate climate risks and develop approaches for managing water resources under uncertainty. Scott and his research group have been supported by the U.S. Army Corps of Engineers, NOAA, U.S. Department of Agriculture, National Science Foundation, and I'm sure some other entities that I didn't include in there. Dr. Steinschneider is also a recipient of the prestigious National Science Foundation Career Grant with a project focused on risk-based climate planning in the Great Lakes. And that will be the topic he'll be talking about today with us. So I welcome Scott to come on up.
Thank you, Steve, for the introduction, and I want to thank the Planning Committee of the Healthy Water Solutions Conference for the invitation to speak today. And what I want to talk about today is a water system that's critically important to New York State. And it's actually the water system that forms the entire northern boundary of New York, and that would be the Lake Ontario St. Lawrence River system. So through this talk, I first want to review what is really the fascinating history of this system and the management of this system, before getting to some more recent events, specifically some severe flooding that happened recently over the last few years in this system that had really negative impacts on the folks who live in this region. I want to talk about and discuss how that flooding prompted calls from the public for changes in how this system is managed to reduce that flood risk. But at the same time, I want to highlight why it's actually pretty complicated and difficult to satisfy those demands, both under current hydrologic conditions, but especially as we look forward to future hydrology under the effects of climate change. And then finally, I want to sort of conclude by taking a step back and see if we can't derive some lessons that we can learn from this system that are more broadly applicable across New York as we think about flood risk management and water resources management more generally across New York. Okay. So for those who are not familiar, Lake Ontario is the last of the 5 major Great Lakes. It's the giant water body directly to the north of us right now. And water in this system flows from west to east. So water starts in the Lake Superior Basin, then flows through Lake Michigan-Huron into Lake Erie, over the Niagara Falls into Lake Ontario. And then finally it's discharged into the St. Lawrence River, right over there, and out to the Atlantic Ocean. And it turns out that Lake Ontario is a managed lake. It's actually one of the single largest managed lakes in the entire world. So there's a dam on the St. Lawrence River, the Moses Saunders Dam, and releases from that dam can influence, at least to an extent, the water levels that we experience on Lake Ontario. Now, the institution charged with making those release decisions and regulating this system is the International Joint Commission, or the IJC. The IJC was established in 1909 under the Boundary Waters Treaty between the US and Canada. And their purpose is really to try to either prevent or resolve disputes on shared water bodies between the two countries. And the management of this system and the evolution of that management, it really is very, very fascinating. And you can actually see it if you look at a time series of the water levels on Lake Ontario itself. And so that's what we're looking at here. So on the y-axis, these are water levels on Lake Ontario, and we're looking at 100 years plus of data going all the way back to 1918. And so there's a lot of features that I want to point out in these data, and the first thing I'll draw your attention to is everything before 1950. So if you look at the water levels there, they're actually pretty variable. And in particular, there's a lot of interannual variability. And what I mean by that is you'll get multiple years in a row where water levels are like higher than average, and then multiple years in a row where water levels are very below average. And if you let the Great Lakes kind of do their thing naturally, these are the types of water levels that you get. But in the 1950s, and specifically 1952, the IJC approved the development of that Moses-Saunders Dam on the St. Lawrence River. And initially, it was designed to meet a few different objectives. It was going to produce a lot of hydroelectricity. There was going to be some water supply concerns that would help support. But the other big objectives is it was going to support commercial navigation, in particular, stabilizing flows on the St. Lawrence and as well as in Lake Ontario to help ships come all the way from the Atlantic up the St. Lawrence River into Lake Ontario and actually to gain access into the interior Great Lakes and therefore the markets of Central North America. And the Moses-Saunders Dam, it was conceived in conjunction with a broader project, which is the St. Lawrence Seaway Project, where they actually dredged out the St. Lawrence and they developed a whole extensive set of canals, again, to support that commercial shipping. So they initially approved the development of this dam in 1952, but actually just a year or two later, there was some pretty significant flooding on the system before the dam was built. And so in 1956, they amended their order and said, okay, we're still gonna build the dam, it's still gonna generate a lot of hydroelectricity, support commercial navigation, but in addition, we'd also like operations at this dam to try to reduce flood risk upstream of the dam on Lake Ontario, and if possible, also downstream of the dam on the St. Lawrence River, or at least don't make it any worse than it was before the dam went into place. Okay, so the dam went in 1958, and they began operating it according to a particular regulation plan or set of release rules, but soon after they started, they ran into the drought of the 1960s. And the 1960s drought was and continues to be the worst drought on record for this entire region. And water levels got very, very low, so they actually had to adjust how they were operating the system to try to bolster water levels and support commercial shipping in the region. And after that point in time, they then sort of like established what the regulation policy was going to be for this dam, and they continued to use it for several decades going forward. So after the 1960s, there's a few other events I want to point out. There's 1960s. So in mid-1970s, there was some significant flooding in the system, loss of widespread coastal damage. And I want to point this out because this flooding happened despite the dam being there and despite some of the operations that the dam meant to reduce that flood risk. So the point is, even with the infrastructure in place, you can still get pretty widespread flooding in this system. After the 1970s, we entered this period from like 1980 into the 2000s of extremely stable water levels where the variability was actually pretty low. And that was actually kind of the point of the dam in the first place because most stakeholder groups like the water level variability to be condensed. But there is one stakeholder group that does not like that condensed water level variability, and those would be the ecosystems that had evolved to a much more variable and natural water level regime. So the way this works is, and this is particularly true for wetlands in the system, and particularly wetlands in the eastern part of the Lake Ontario Basin, they had evolved such that you could occasionally get some really high water levels. Those would flood out some species, and then when the water levels dropped, they would expose seed banks and new emergent wetland species could come up. And so you would get this very dynamic and diverse wetland ecosystem. Now, when we condensed the water levels, all that basically went away. And particular species came to dominate, and especially, and this is what the picture is showing, cattails were able to march right up to the shoreline and choke out everything else. So that's what this picture is showing, and it's not supposed to look like this. The wetlands are supposed to look like a much more diverse ecosystem that supports a lot of flora and fauna. So when scientists became aware of this during this period, and the IJC became aware of this during this period, that sort of kicked off what turned into like a 15-plus year process, significant studies, deliberation, and debate about whether or not they could come up with a new water level management plan for this system that could increase water level variability a little bit to help restore these wetland ecosystems without messing up any of the other objectives, so without detracting from flood risk or commercial navigation, hydropower generation, and the like. So after a very long process and back and forth, a lot of things happened in there, but at the end of the day, the IJC came out with a new regulation plan that they called Plan 2014, named because that was the year in which it was established. And it's important to note that this plan, which again was meant to increase water level variability a little bit for ecosystem benefit without detracting too much from other stakeholder groups, not everyone was on board with this plan. In particular, stakeholders, especially in New York along the coastline of Lake Ontario, they were concerned that that increased water level variability would increase their flood risk and also increase their risk to low water levels that would sort of reduce their access to the lake, which is necessary to support recreational boating, which had become a very significant portion of the local economy. Okay, but anyway, Plan 2014 went forward, and that brings us to the more recent period. So I'm going to zoom in on that shaded area there. So now we're still looking at water levels, but now it's from 2016 to 2019. And so it's a little confusing. Plan 2014 actually went into operation in January of 2017. That's when they started to use it. And so that's that dotted line right there. And then 6 months after they started operating the system with this plan, not even 6 months, there was record level flooding, highest water levels in over 100 years. And then 2 years after that, in 2019, that record was broken again. And so needless to say, there was extensive damage along both Lake Ontario and on the St. Lawrence River. Homes were falling into the lake, massive erosion, lots of inundation. And understandably, the public was pretty upset. And they blamed Plan 2014 for this flooding. Now, the IJC pushed back on that, and independent experts also pushed back on that and said, look, we know it looks terrible, but this was just really, really bad timing. We started Plan 2014 in January of 2017, and that actually started the wettest 3-month and wettest 6-month period ever observed in this region. So the argument was it was just the massive amount of excess precipitation that actually led to flooding. Other plans would have also had flooding occur too. Most folks did not buy that argument, and there was a significant amount of what turned into political pushback. So for instance, the state of New York, after the 2019 flood, ended up suing the IJC, saying that they were not meeting, they failed to implement their flood control protocols under the plan. Now, I don't think this lawsuit went anywhere at the end of the day, but it sort of highlights the political pressure and just frankly the public anger that the IJC was under. And so in response, they initiated an expedited review for the water resource management plan of the Lake Ontario St. Lawrence River system. And the group that actually helped lead that review is the Great Lakes Adaptive Management Committee, or the GLAM Committee, as well as the Lake Ontario St. Lawrence River Board of Control, who actually regulate the releases from this system. And the GLAM Committee, they're composed of engineers and scientists from the Army Corps of Engineers, from NOAA, from Environment and Climate Change Canada, as well as experts from ministries in Lake Ontario and Quebec. So this is actually where my lab came into the picture here. So we developed a partnership with the GLAM Committee to try to answer the question, can we find a better regulation plan than the one that they just started to operate with, Plan 2014? And it turns out that it's actually pretty difficult to answer this question, and for a few reasons. One of which is we actually have to, what do we mean by better? So one way you can think about better is you can come up with an operational plan that leads to better outcomes for everybody. You can reduce flood risk upstream of the dam, reduce flood risk downstream of the dam, improve commercial navigation, improve hydropower production, improve ecosystem outcomes, improve recreational boating outcomes, right? And that would be wonderful. But it's reasonable to ask, is that even possible? And if it's not, maybe the way we have to define better is maybe we want to reduce flood risk, but we have to give up some of the benefits for some of those other stakeholder groups. And if you do that, how much are you willing to give on some to help improve the outcomes for others? And the fact of the matter is that's not a quantitative question. That's a societal values question. If you ask 10 different people, you might get 10 different answers to that question. So that makes this a very complicated thing. And in addition, we also, when we wanted to find a better plan, better under what conditions? So traditionally, when we design these water resource management plans, they've traditionally been designed to operate well under historical hydrology and climate. But there is the expectation that the stuff that we've seen historically may no longer be indicative of the things that we're going to have to deal with hydrologically going forward. And so do we still design these water resource management plans for the last, let's say, 100 years of climate? Do we try to tailor it to maybe the last 30 or 40 years, which maybe is more indicative of what we can expect going forward? Should we just tailor these plans for what we project to happen in the future, either in the near term, 2030, or maybe a little further out, 2050, 2070? Or do we want a management plan that kind of can do it all? And again, is that even possible? So these were the sorts of questions that we were grappling with and trying to deal with as part of this project. And so going forward in the presentation, I want to show you some of the outcomes of the work that we did at Cornell, trying to answer some of these questions. And at this point, there's an important disclaimer or caveat I want to put out there. Everything I'm about to show you is work that we did at Cornell, which is a research project in support of and complementary to the broader and larger expedited review that the GLAM committee was running. But the things I'm about to show you are Cornell's work. They don't reflect the points of view or the analysis of GLAM or the IJC. It's an important point for me to just make very clear. Okay, with that said, I want to show you what we did. Okay, and to do that, I actually want to highlight 4 different things as I go through that process. The first is, I've talked a lot about regulation plans, but I imagine at least some of the audience are like, okay, what actually is a regulation plan? What does that actually look like? So I want to take a moment to just show you what a regulation plan actually looks like. And if we have a regulation plan, how do we know it's helping or hurting different stakeholder groups? So the next thing we got to do is we have to somehow quantify the impacts of these regulation plans on all of these different stakeholders. I want to show you kind of how we do that. And once I do that, then how are we going to find new candidate promising regulation plans that we might want to consider over the existing plan? What are the methods we're using and the new technologies we're bringing to try to find those alternatives? And then finally, what I want to end with is how are we going to address issues of climate change and make sure that any regulation plans we identify are robust under a broad range of plausible futures that we might have to deal with going forward into the future. Okay, so let's start with the first one. What is a regulation plan, really? So a regulation plan is just a set of rules that tell you what releases you should make from that dam at any given point in time, given the state of the system. So for instance, if I'm sitting at the dam, I can look at the water levels in Lake Ontario at that time, and I can look at the water supplies entering the lake and the rest of the system at that time, or maybe a forecast of those water supplies. That's the state of the system. And given the values of those variables, I might have a set of rules that tell me make this release. So here is a really simple regulation plan. Sometimes I'll call it a control policy, this set of rules. So in the one I have here, it says, if the water supplies in the system are really high, greater than 9,000 cubic meters per second, and if the water level is also pretty high, greater than 247 feet above mean sea level, release a lot of water, release 10,000 cubic meters per second to try to draw the lake down. Otherwise, release much less water, 8,000 cubic meters per second. Now, this is a super simplified, highly stylized regulation plan, very unrealistic, but here's the actual snippet of the thousands of lines of code from the actual regulation plan. I don't expect you to see anything in there, but if you squint, in orange, you might see some ifs and elses. So the only thing I'm trying to highlight here is that this basic structure, this if-then-else structure, is kind of how these regulation plans are designed. They're just more complicated and more rules. Okay, so if we have that regulation plan, and we'll use the dummy one here, we can actually simulate what the water levels and the flows in the system would be following these rules. So I'll sort of show that to you with these 3 plots here. So here on the upper left, we have the water supply entering the system. Here's the water levels in Lake Ontario. And here are those release decisions, the outflows from the system. And on the x-axis in all of them is time. And so what I'll do is I'll throw on those thresholds, 9,000 cubic meters per second for water supply, 247 feet for water level. And we can literally start marching through time following these rules to determine what the outflow should be. So for instance, let's say we start here. Our water supply and water level is less than those thresholds. So we release 8,000 cubic meters per second. And if you squint, you might see that the water supply is a little higher than 8,000. The releases were 8,000, so the in is bigger than the out. So the water levels are going to rise a little bit. So if we go to the next time step, you see the water levels rise. We're still under the threshold, so we're still releasing 8,000, so we're still going to continue to rise. Water supply now has gone above that threshold, but the water levels are still below, so according to our rules, we're still releasing 8,000. We continue to rise. And then once both of those indicators grow above the threshold, then we kick up our releases to 10,000, and now they're higher than what's entering the system, and so we'll start drawing the lake levels back down. And that will continue until we drop below one of the thresholds for one of the variables, and we go back to the lower set of releases, right? That's basically how these simulations work, is just a more complicated set of rules.